subscribe.
Hey y'all, welcome back. So today we are going to finish our last day of algebra review, and today we're going to be looking at two concepts. We're going to look at how to combine functions and also how to compose them. So when I talk about combinations of functions, what I'm referring to is either adding, subtracting, multiplying, or dividing two different functions. In essence, when I combine functions, I'm really just combining them with an operation. When I'm talking about compositions of functions, instead of either adding or subtracting them using an operation, we're going to be combining them by substituting one function into another. And we'll get into some pretty good detail trying to explain that in a bit. But for now, let's take a look at these different combinations. Like I said, this is when we're either adding, subtracting, multiplying, dividing two functions together. So let's say we had f of x equals 2x plus 3 and g of x equals x squared minus 1. So we've got these two functions, and we're going to combine them using the four different operations. So if we add these two functions, you do pretty much the same thing as you would have done like in Algebra 1, where we're essentially just combining like terms here to make this a little clearer on what's going on here. If I say f of x plus g of x, I'm going to put parentheses around here even though you don't really need them. But here we're just going to combine like terms. So we're going to be left with x squared plus 2x, and then negative 3 minus 1 would be minus 4. So this is this function represents f of x plus g of x, and we do have a little bit of a more efficient notation for a sum of two functions, and so you might see that written like this, where it's f plus g of x rather than f of x plus g of x. We can do the same sort of thing with subtraction as well. This is another way we can combine functions. And it'll work pretty much the same way, except we're going to be subtracting instead of adding. And here's where the parentheses are a little bit more important here, because you do need to make sure to subtract each term in the second function. So when we combine these terms, we're going to get negative x squared plus 2x, and then negative 3 minus negative 1 is going to be minus 2. So just like with addition, we do have a more efficient way of notating f minus g of x, or f of x minus g of x, and it looks like this. So more often than not, I'm going to start using this notation rather than separating them out like this. We can also multiply functions, and if you just have two binomials, like in this case, 2x minus 3 times x squared minus 1, you can multiply them out by foiling, or you can just think about the distributive property and how that generalizes to polynomials. Especially when you have longer polynomials, it might be easier to think about it as the distributive property. Sometimes you'll have functions that aren't really going to be able to be multiplied or simplified together when you multiply them. Like, let's say you're going to multiply the square root of x times sine of x. There's not like anything you can do to simplify that, but in this case we can. We're going to multiply each term on the left polynomial by each term on the right polynomial. So we're going to end up with 2x cubed minus 3x squared, minus 2x plus 3. And so there's nothing left for me to combine here, so that would be it. Just like with addition and subtraction, we've got this alternative notation that you're going to start seeing, just f of g of x, or not f of g, but f times g of x, which you can write instead of f of x times g of x. Lastly, we've got this division combination where we're combining functions using division. And in this case, and most of the time, you're not going to be able to simplify anything when you divide. You're just going to be left with the top function divided by the bottom function. And yeah, so sometimes you can simplify it. Like if there's a common factor, you can reduce out to 1, but most of the time, you're just going to be stuck with whatever you started with. And just like with the other three functions, we can write that a little differently. So instead of writing f of x over g of x, you're going to more commonly see f divided by g of x. So this is going to be how you combine functions given an equation, but you can also combine functions given a graph. So let's take a look and see what we have down here. So here we're given the two functions that are graphed, f of x and g of x. We're not given the equations explicitly, although these are pretty simple graphs, so we could come up with the equations. But I want to show you how you can graph these without coming up with f of x or g of x separately. So if we're trying to find f plus g of x, really all you want to do here is you're going to pick x values where you can clearly see what the y values are, and then just add them. Okay, f plus g of x really just means f of x plus g of x, or another way to think about it is at any given value x, f plus g should be the y value of f plus the y value of g. So if x is -3, for instance, right here, the y value of f is 6, and the y value of g is -1, so 6 plus -1 would be 5, and we can plot that on here. And then we can go through each of these x values and do kind of the same thing. So if I want to know what is f plus g of -2, right, here's where x is -2, I can add 0 plus 1 and get 1. And I'm just going to continue that process until I run out of points. So if I look at x equals -1, I get 1 plus -2 is -1. If I do, let's see, 2 plus -3, that would also be -1. Whoa, point doesn't need to be that big. If I look at, when x is 1, right here, I see that I've got 3 plus -2, which is +1. You can start to see a little parabola being generated here. If x is 2, we get 1 plus 3, which is, wait. Is that right? 1 plus 4 is 5. So we'll put up here, and I'm not sure if the last one's going to fit here, but we get 5 plus 6. So yeah, it's going to be a little off the grid here. So we can see that we do have a parabola. I'm going to do my best to draw this with a mouse. It doesn't look that great, but you can kind of get the point here. So yeah, there we go. We get a parabola. And actually, if you do find the equations here, which you don't have to do, it's not asking you to do that, but if you look at these graphs and you see, oh, well, f of x is actually, x squared minus 3, and then g of x, you can see is a linear function, and it would just be 1x plus 2. If you combine these two functions to get x squared plus x minus 1, and you graph that separately, you should get the same graph. Okay, so you don't need to do this, and especially when the functions are more complicated or maybe not as well defined as these two, you really just want to go based on the points that are graphed on there. You can graph f times g using this same method. Just remember that we're going to be multiplying the y value of f times the y value of g. So we're going to go through each individual x value like we did over here, and we should be expecting a cubic because we're multiplying a quadratic times a linear. So like if I FOIL these two out, my first term is going to be x cubed. So it's going to be okay if my graph goes like up and down and then up again. We should expect that. So let's just see how that'll actually play out here. If x is -3, we've got -1 times 6, so that's going to be -6. Let's see here, -3, -6. And then we've got 0 times 1 is just 0. And then 1 times -2 is -2. So we're starting to see this cubic action where it goes up and comes back down. Probably going to go back up again. So when x is 0, we've got 2 times -3, so that's -6. And then we've got 3 times -2, so that's -6 again. All right, okay. Kind of weird, but all right. And then we've got 1 times 4, so that's going to be 4 all the way up here. And then we got 5 times 6 is going to be 30, so it's going to be way off the page. So we actually are going to get something that looks like this. Okay, so it does kind of look like a cubic. If you were to multiply these out, you would get, you'd start off with x squared minus 3 times x plus 2. And if I multiply those out, I get x cubed plus 2x minus 3x minus 6. And this does have the correct end behavior and the y-intercept and all that. So let's see, our x-intercepts would be, we'd have one at -2, which checks out, and then we have 2 at plus or minus root 3, which kind of looks right. So I'm pretty confident this is going to be correct. So anyway, you don't have to find this equation. You can just go point by point, but you do want to be thinking about what type of graph you're going to end up with. So like if I just plotted these points separately, it might not be super obvious what the curve should look like, but if I know it's a cubic, I can expect it to kind of go up and then down and then back up again based on what the end behavior and y-intercept should be. So anyway, this is how you're going to combine functions. It's not too terribly complicated, but what I really want to get into today, which I think is more important here, is how to compose functions, how to come up with a composite function. So a composite function is one in which you take one function and you substitute it into another. And the notation here is going to be unique. We haven't seen this before, unless you saw it like in Algebra 2 or something, which you probably did. And we're going to use this symbol right here, this little open circle here, as the composed with symbol. And so when you see this, this is really all it means, is if you see f of g of x, which is how you would normally read this, what that means is that you're plugging in g into f. So if you're kind of following like a domain range chain here, you're going to take your original x values, plug them into the g function, and those will output some values, right? Like the y values of the g function. Take those y values and plug them into the x values for f. And then what you'll end up with is your final outputs there would be f of g of x. So basically you're substituting one equation into another. So here's a couple of functions, and I just want to kind of practice going through these with you so you can kind of see, what do I actually mean here? So we've got three functions. We've got f of x is 2x plus minus 5, g of x, which is negative 3x squared plus 7x minus 5, and h of x, which is the square root of x. So let's take a look at this one, f of g of x. So what this really means is that we're going to take g and substitute it into f. Okay, so we're going to take the g function and we're going to plug this in everywhere where we see x in the f function. Okay, so in other words, like we're going to have, f is 2x minus 5, but if we substitute the g function into x, we're going to get negative 3x squared plus 7x minus 5 in place of that x. And then from there, you're just simplifying. So nothing too crazy going on afterwards. We'll distribute, we'll combine our like terms and so on. So nothing too wild going after that. But the real key to understanding compositions of functions is that you are substituting one function into another. Okay, so we end up getting negative 6x squared plus 14x minus 15. So yeah, let's do a few more, and just so you can kind of start to get a feel for how you would actually evaluate these. So the second one is g of f of x. Now, the order here, it matters. So you can't just necessarily, if you've got f of g, you need to plug g into f. If you have g of f, you got to plug f into g. So you have to make sure you're plugging the correct function into the correct one. So the one that's getting plugged into the other one is going to be on the inside. So here we're going to substitute f into g. You can think about this, as its more conventional notation, g of f of x. So we're going to substitute f, this 2x minus 5, into every instance of x. And this one gets a little trickier because there are multiple instances of x in the g function, right? Because it's negative 3x squared, plus 7x minus 5. Notice here we've got two x's here. So we've got to substitute f into every instance of x. So we're going to plug 2x minus 5 here. And we're also going to plug in 2x minus 5 here. Okay, now we do need to simplify this a little bit, but I'm not too worried about that, to be quite honest. That's not really the focus here. I'm going to assume that you guys can, kind of follow along and do the multiplication and the simplification rather. Trying to do this while I talk is not as easy as I thought. But yeah, so we got to multiply. We got to FOIL out the 2x minus 5. We've got to distribute the 7, and I'm doing this while I'm talking, so it's possible there's an error here somewhere, but I feel okay about it. So we got plus 60x minus 75, and then at this point, we are just going to combine our like terms. So we get, let's see here, negative, there's no more x squareds to combine with. We've got a plus 60 plus 14, so that'd be plus 74x, and then minus 75, that'd be minus, let's see, what would that be? Gosh, I'm drawing a blank here. Okay, minus 115, I think. 25 would leave 15 left over. Yeah, so minus 115. You might want to double check my arithmetic there, but the overall idea here is that you're going to substitute f into g. So if you're trying to evaluate one of these composite functions by figuring out like f of g of 2, for instance, like if you want to know the specific value of the function at a given x, there's two ways you can approach it. One is you can plug in 2 into g, so plug it in like up here, wherever you see x, so you'd have like negative 3 times 2 squared plus 7 times 2 minus 5, and then take that value and plug it into f, or you can find f of g separately, like we did up here, and then just plug in the 2 here. So I think the first way, where you're plugging in 2 into the original function, the inner function, and then plugging that into f, is usually going to be easier so that you don't have to find the actual function f of g. But if you have already found what f of g is, then we're just going to evaluate that at 2. So we're just going to substitute 2 into this function. Either way is acceptable, and honestly, it doesn't really matter. If you find it easier to just go ahead and evaluate the function, figure out what is f of g first, and then plugging it in, that's fine. That's what I'm doing here. However, if that's a little bit too much work to like go through and figure out what this is, then you can just put 2 into here, get a number out, and then plug that into here. 2 times whatever you get for g of 2 minus 5. Okay. Well, another way you can kind of think about this is you're substituting whatever you get for g of 2 into f. So if you already have f of g, if you have the composite function already, or f composed with g here, then we could just substitute in 2 like we're doing. So we get negative 6 times 4. Let's see if we can just evaluate this at once here. No calculator here. Okay, so 2 squared is 4, and negative 6 times 4 is going to be negative 24. 14 times 2 is 28, and so now we just got to combine. So 28 minus 24 is going to be 4, and 4 minus 15 is going to be negative 11. Now if we want to do g of f of negative 1, we're going to do kind of the same thing. This is equivalent to saying g of f of negative 1. So same thing that I was talking about earlier, where you could plug in negative 1 up here. You get negative 2 minus 5, which would be negative 7, and then plug in negative 7 into g. And you'll get the same thing as if you were to just plug in negative 1 into the g of f function. Sometimes plugging that into the original functions is easier because your numbers are smaller. But at the end of the day, you'll get the same, as long as you do it correctly, you'll get the same value. So if I plug in negative 1 here, and here, I can start to evaluate here. Negative 1 squared is just going to be 1, and 1 times negative 12 is just going to be negative 12. 74 times negative 1 is just going to be negative 74, so we'll change that to a minus. So now we've got these 3 numbers to combine. Oh, these numbers are getting kind of annoying here, but let's see if we got this. So we got 12 and that'd be 80, 86, and then combined with the 115. Okay, well I'm going to split this up, make this a little easier on myself. So that'd be negative 186 minus 15. So if I do minus 14 minus 1, I'm splitting up that minus 15. I'm just trying to make it easier for myself. So it's going to be minus 201. And you could, just as easily put that in the calculator. I'm just trying to avoid that because I don't think it's really too necessary here. Okay, so the next question says determine a function n of x such that f of n of x equals x. Okay, so we've got f of n of x. So I'm going to rewrite it like that. So this is the equation we're trying to find n. And so f is 2x minus 5, right? So we've got 2 times whatever this n of x is, this unknown, minus 5 equals x. And what we want to do is we want to solve this for n of x. That's going to be our n. So we're going to add 5 to both sides. And then we can divide both sides by 2. So we get n of x equals 1/2 x plus 5 over 2. So that would be our function there. So you can use this to solve for this like unknown function. Now, this is one technique you can do. Not really getting into this today, but if you have a function composed with another function and the result is just x, what's kind of cool about this is that means this is your inverse function. This is the inverse of f. So f and n are inverses here. This is an alternate way of finding an inverse function versus like swapping x and y and solving for y. Actually, I kind of like this. I might use this next year. But anyway, so this is just another way of finding that. Now that's where it gets a little tricky. This really is going to test your ability to understand like what is a composite function and how do we actually evaluate these. So what you really want to do here is you want to work from the inside out. You're going to evaluate what's inside the parentheses first and then use that to substitute into the outermost function. So this is equivalent to saying like, fog2, f of g of 2. I don't know if I'm going to have that composite symbol here in Cami. I don't. So I would just have to write it. So it'd be like f, I'll just write it for this first one just to kind of give you one to look at here. F of g of 2. Okay, so I could write it either way. This means the same thing as this. Let's see, did I throw a parenthesis? Yeah, I did. Okay, so the way we're going to evaluate this is first we're going to find g of 2, and then we're going to plug that into f. So we've got two different tables, one for f, one for g, and we're just going to kind of look at these systematically. So this is going to equal f of, and then g of 2, so we're going to look for where x is 2 and report back the y value, or the g value, which is 3. So g of 2 is 3, and now we're going to evaluate f of 3, which is 9. And we can find that from the table, right? If x is 3, then f of x is 9. And we're going to go through that process for each one of these. So f of g of 1, so g of 1 is 9, you see that right here. And f of 9 is 6. You see that in that first row of the f table. Okay. G of f of 6. So we're going to first evaluate f of 6, which is 7. And so now we're going to say g of 7 is, let's see here, 4. So now these should be designed so that we can actually find all these values. So if you're kind of working through these and you find one that's like, it's like not on here and this doesn't really seem to have any pattern or discernible function, that rule, then you probably did something wrong. Okay, so here f of 12 is 5, so we're going to say g of 5, and g of 5 is 6. So this equals 6. I'll throw in a couple of boxes here just to kind of clean this up. The next one is f of g of 7. So we're going to first evaluate g of 7, and then we'll plug that into f. G of 7 is 4. You can see that in the second row here. And then f of 4, going to have to hide this, is negative 3. This will equal negative 3. For g of f of 3, we're going to substitute 3 into the f function, and we'll output 9, so that'll be equal to g of 9. And then g of 9 is 12. So that's how you can use a table to evaluate these composite functions as well. Just like with any other functions, we can evaluate them using an equation like we did up here. We can also evaluate them using a table. And finally, we can evaluate them using a graph. But it's the same idea where we're taking one value that we get from one function and plugging it into the other. So let's just run through these, and I think that's it for today. So it says first f of 0. So no composite function, just what does f of 0 equal here? It says f is this first function up here, g is this second function down here. So f of 0, we're going to go where x is 0, and the output is 8, okay, right here. So g of 0 is 2. F of 3, so 1, 2, 3, is going to be negative 1. Oh, not negative 4, negative 1. G of 2 is 0. Okay, those are kind of boring. Let's get into the composites. This is a little bit more interesting. So here we're going to find f of g of 2. So let's first find g of 2. G of 2 is 0, and so now we need to evaluate f of 0. So f of 0, we already found that. It was 8. G of f of 0. So f of 0 is 8. So we want g of 8. And then we look at the g function and notice, hey, it's just not on there. I know earlier I said, hey, these should be defined well, but sometimes they're not. So in this case, g of 8 is not defined, so that's all we're going to say. It says undefined. Okay, there's no output for an x value of 8 here for the g function. For f of g of 4, first we're going to evaluate g of 4. So we're going to look at the x value. We're going to look at where x is 4 in the g function. And let's see, when x is 4 for g, the y or the g value is 4. So now we're going to evaluate f of 4, which if we're looking up at this graph, we get 0. Then g of f of 1, we're going to evaluate f of 1, sorry. So g of, let's see what f of 1 is. F of 1 is 3, so we're going to evaluate g of 3. So g of 3, 1, 2, 3 is going to be 1. Okay, so you just basically you're going to just evaluate the innermost function first, take whatever you get there and plug it into the outer function. When does f of g, so here's where another one where we're kind of solving an equation here. F of g of x equals 8. What x value will make that happen? So first we want to know, when is f equal to 8? Well, f is equal to 8 when x is 0. Okay, in other words, we're looking for the x value when y is 8, and that happens right here, right here. So that means that g of x needs to be 0, because if f of 0 is 8, then g of x needs to be 0. And then we look at the g function here and say, okay, well, where is this equal to 0? Right, where are my outputs 0? So here I see there's actually two of them. There's one right here, really obvious, it's at x equals 2. And then we have another one that's not as obvious, right, where x is, looks like about negative 1.5, 1.3 maybe. Hard to tell, but we'll just estimate that, okay? So we're going to get x equals 2 for sure, and then x equals approximately, because we don't know the function yet, and I'm not going to make you find the function here, but we know that x is approximately negative, I'll call it 1.3. It looks like it's not quite at 1.5, so I'll call it 1.3 and just kind of call it a day there. So if you got to estimate, that's fine. Know that on some of these, it's not going to be super clear, and so if you just give a rough estimate, that's good enough. It says give an x value for this last question where the function's undefined. So in order for f of g of x to be undefined, we need to find a place where f is undefined, okay? So f is undefined whenever it's greater than 8 or less than negative 1. So what we want to find is, here, let me make a little note here. F is undefined when x is greater than 8 or x is less than negative 1. Okay, so what that means is that g of x either needs to be greater than 8. Now, we don't have a point that's greater than 8, so we can ignore that one. But we do have some values where g is less than negative 1, and we can see that's happening clearly right here. So it's happening whenever g of x, we can say if g of x is less than negative 1, like when x is negative 2, But basically, any value, so this will be any value or let's see here, when g is less than -1. Yeah, so basically we want a value that's down here. So probably there are infinitely many correct answers here, but I think the way to go here, the most clearly defined one is going to be x equals -2. So when x is -2, we could do g of x. So g of -2 is -2. And then, oh, wait a minute. Oh, yeah. So, okay, so sorry about that. So x is negative, sorry, if x is -2, g of x is -2. And then so f of -2, you can see, is undefined. There's nothing going on over here. So anyway, that's it for today. Kind of a weird question at the end here, but hopefully you can think your way through it. If not, as always, please reach out and ask me any questions you have, and I can try to clarify anything. But y'all have a great day, and I'll see you next time. One quick little addition here. I made a little typo here. I was saying that f is undefined, the value of f is undefined above 8 or below -1, and I wrote that as x, but this should have been f. Just a little correction here. If I'm going to say it in terms of x, I would say that x is undefined when it's less than 0 or greater than 5. So my bad here. I think I said it right. I'll have to go back and check, but I just realized I typed this incorrectly. So f is, I'll say, really to just kind of make this as clear as mud here. F of x is undefined when x is less than 0 or x is greater than 5. So the other way I was talking about the value of f, like the output of f, there's no definition for f above 8 or below -1, but that should have said f is less than an f. If we're talking about x, it'll be less than 0, greater than 5. This answer is still right. I think I was explaining it right, but I definitely typed this out incorrectly. So nice little correction here. At this point, y'all can have a great day. I'll see you next time.